If you grab something small, say an eyeball that contains mysterious magical properties, and toss it into the air, what would happen? It would go up into the air and come back down, right? Everyone knows this. But why? Why is your hand able to support the eyeball? Why are you able to throw it? Why does it come back down? Let's take a dive into the 3 laws that make the world of physics go round. The eyeball was still before you picked it up. Why is that? Well, we can attribute that to Sir Isaac Newton's first law of motion. The law states that unless acted on by an unbalanced force, an object at rest will remain at rest. Here are the forces acting on the eyeball. There's gravity pushing down on everything. There's the eyeball pushing down against the table, and there's the table pushing back up against the eyeball. Since your hand has a greater force than the eyeball, making it an unbalanced force, it was able to put the eyeball into motion. Your hand picked it up, changing its position. Imagine you accidentally shook the flat, smooth table that the eyeball was on. The eyeball would have rolled a bit, right? But would a large and potentially magical geode have moved? Probably not. At least not as much. Why is that? Well, first we need to understand what inertia is. Inertia is an object's natural tendency to resist motion. The more mass an object has, the greater its inertia is. Because the eyeball is small, light, smooth, and round, it doesn't have a lot of inertia, and the smooth and flat table that it resides on doesn't provide much friction, which is a force that resists motion. However, friction and inertia aren't the only reasons for the difference in motion. Let's take a look at Newton's second law of motion. This law states that force equals mass multiplied by acceleration. How is this relevant? Well, the acceleration in this case would be the movement of the shaking table, and the masses would be those of the eyeball and geode. Since the geode has a larger mass than the eyeball, the force that it puts against the table is greater, and this is counteracting the force of the shaking more than the eyeball's mass is. Imagine you had a potion bottle that was completely full. If you rolled the eyeball against it, not much would happen. The eyeball would probably roll back after hitting the bottle, and maybe the potion inside the bottle would move a bit. But what would happen if you threw the eyeball at the potion bottle? The bottle would probably get pushed back and wobble a bit, and maybe it would fall. The eyeball would probably bounce off the potion bottle. But why? Because of Newton's third law of motion. The third law of motion states that every action has an equal and opposite reaction. The actions in question were rolling and throwing the eyeball against the bottle, and the reactions were the potion maybe splashing a bit and the potion bottle getting pushed back and maybe wobbling a little. Now, what makes these equal? Well, the reason the eyeball bounced back off the potion bottle is that the potion bottle reacted with the same amount of force as the eyeball hit it with, making it bounce. The same thing happens when you jump. And that's Newton's 3 laws of motion. My sources were my science textbook, and that's it. Thank you to my mom for playing the supporting role of the hand and helping with the composition of the set. Thank you to me for directing this and coming up with the idea. And thank you to Miss Pauline for giving me the science project.